Hello everyone, this is Spencer Snolling from Hydromantis, and I'm glad that you could join us today for our usual GPSX webinar where we're going to be talking about the Sankey diagram feature as part of GPSX and how you can use it to understand the the mass flow of nutrients around your wastewater treatment plant. This is a new feature. Well, not that new. I guess it's been in for a couple of years, but it's one that I've been learning to use more as part of my reports and part of the analysis that I've been doing over the years, and one that I found to be actually quite useful when describing the results of my modeling work to other people. Okay, so I'm Spencer Snolling. I'm VP of Product Development here at Hydromantis, and I'm glad that you could join us today. The agenda is to just sort of introduce the concept of what a Sankey diagram is, talk about how to actually use it in GPSX, how you generate it. You can make some changes to it, customize it, and we've put in a number of features to be able to export out all of the information that comes from a Sankey diagram. And also, of course, as usual, I'll share my desktop here and demonstrate how to use the software. And as always, we'll answer any questions that you might have when we get to the end of the webinar. What I usually like to do is have you type them into the questions box as part of your GoToWebinar dashboard. So just feel free to type those in as the webinar is proceeding, and I'll see those come up, and then we'll tackle them when we get to the end. Okay. So Sankey diagrams are actually named after H. Ryle Sankey, who is a Irish steam engine engineer and developer from the mid to late 1800s. The name kind of came to be associated with him based on a single publication, actually, of discussion of thermal efficiency of steam engines, and he produced this particular diagram, even though the concept itself had sort of been illustrated by other people prior to that. This was the first time it had been sort of, I guess, widely accepted and widely used in an engineering context to understand the flow. And in this particular case, it's talking about flow of heat and the flow of energy as opposed to nutrients, like we'll be talking about in a few short minutes. But the idea is the same. Basically, you have a way of keeping track how things flow through your system, and it's done through having this sort of large line here that divides off into parts and goes to other places, and you can fold in recycles and so on here. So in this particular case, he's talking about the amount of heat that's generated from this fire that goes through this boiler system and through this pipe, and in each place you can see there's a little bit of loss, radiation through the boiler, and there's like friction losses and so on, and it gets here to the actual engine, and some of that is actually used to produce some output here, and there's other losses and recycles, and quite a bit of that waste heat comes down here through the condenser, and some of that information, or some of that heat goes back to the recycled back to the system as well. So it's a nice way to very visually interpret the information, a lot of information that all has to add up, and just like you have an energy balance or a mass balance, you need this system allows you a very nice way to represent that. So it's very useful for concisely summarizing pathways through of components as they move through a particular system. And as I mentioned, the key feature is that the thickness of the line corresponds to the flow of that particular element. So you may find as you're moving here, as that energy diagram illustrated, that some of that energy was peeled off and lost to the system or was recycled back. That works just really well for something like wastewater treatment, where it's a number of unit processes that are hooked together in series or in parallel and has splitters and combiners and so on. Works well for looking at the hydraulic flow, even before we get to talking about concentrations or masses, even just understanding how the flow moves through your plant. It also works for mass, so in this case we can plot very easily COD and total nitrogen, total phosphorus, that sort of thing, as it goes around through the plant. And I've seen it also used for other things. And in fact, when I was putting together these slides for the webinar over the past couple of days, I found a really fascinating use of it in a military context, a very interesting plotting in a Sankey diagram type format of troops moving across Europe as Napoleon was moving to Russia, and they plotted sort of a Sankey diagram versus elevation. It was quite neat. That actually predated Sankey's diagram that I showed you earlier. So as I mentioned, it's particularly useful wastewater treatment systems, anything that's made up of a series of interconnected parts where flows can combine together and split and move around. And we can do it here for any flows, solids, nutrients, just about anything that you have that's tracked throughout the plant. So any place where you've got one of our connection points, if that number is calculated all the way around through the system, you can actually see it flowing from one place to another. So we've got a tool now that we've built in there. Just with the click of one button, you can automatically generate a Sankey diagram from various types of components. And the way that that's done is once you've built your plant, you've put it together, you've run a simulation, and it's come to convergence, and you've come to the end of your simulation, you can click on this red diagram there that's supposed to sort of look like a Sankey diagram arrow where it's splitting off into different parts. Once you hit that, it'll bring up a new window that looks like this. Now, one thing I'll just quickly mention here is that what you're going to see is the results for the end of your simulation. So if you're running steady state, that's great. That's probably the best interpretation of what a Sankey diagram can do for you because everything will nicely balance. If you are running a dynamic simulation where you've got things turning on and off or something, say like an SBR, what you're going to get in your Sankey diagram is whatever was the condition at the very end of the simulation. So just keep that in mind when you're using this. But all the diagrams that I'm going to show you today were ones that are generated from steady state simulations. So as you can see here, it picks up the GPSX layout image that you have, and it overlays the arrow as it's being calculated. And you can see here where it splits, and we've overlaid a lot of values here that are for whatever thing that you are plotting. So in any case, you'll have a value for every one of the streams in your layout, and this is going to be a mass flow in most cases. And then the thickness of the line that is lying underneath that is proportional to that value. So it kind of looks at what's the highest value in the layout, makes that a thickness that you can control, and then it makes it scales all of the other lines proportionately. So there are a lot of options that you have across the top of your Sankey diagram. You can choose to display or not display various parts of it. You can select which variable that you want to display. And this feature here is for controlling some of the details about the thickness of the line and the color of the line and so on. And I'll demonstrate those for you here in a moment. And then also you can export all of this information very easily just by either printing it directly, or this copy value, the copy button here allows you to sort of copy that image very easily to paste it directly into a report. The other thing that you can do is actually display this for many different variables throughout the system. Now in your version of GPSX that you have right now, you'll note that there is going to be flow, TSS, COD, nitrogen, and phosphorus. And I've added for my own version here on my laptop ammonia. And that's just to highlight the fact that actually you can customize this list here and add various other things that you would like. And I'll show you how to do that at the end of the webinar today. Okay, so probably the easiest thing to do is for us to just immediately jump right to the demonstration. So this is my typical layout that I've put together here for this particular plant. Now I'm using the default sizes in GPSX right now. So this is a half an MGD flow. So it's a very small plant, but everything's sized proportionately. And it comes in here, we have an alum dosage unit that's actually set to 0 right now. So as we're starting out, we're not actually doing any chemical dosage. Through a rectangular primary clarifier with some wasting over here to this thickener. We have a plug flow bioreactor, some secondary clarification. We're taking the wastage to that same thickener, an effluent, and then the thickened sludge is taken to an anaerobic digester. All of the other overflow from that thickener is taken back around to the head of the plant. Okay, so let's just start out by running a default situation here. I'm just completely fully aerating in this tank. There's nothing special, just regular extended aeration. So let's generate the Sankey diagram for that. So if I click here on this button, we can see here that it comes up with this diagram as it is. Right, so what we're looking at this point here is flow. That's the variable that is up here, and we're looking at that in units of MGD. And you can, of course, change to whatever other units you like. So let's just change it to that unit just for fun. And we can see very easily, just looking at flow to start with, that the majority of the flow that comes in the plant goes out of the plant. And there's, of course, our RAS recycle here. So this is a little bit thicker right in here. And then we have a very proportionately small amount of flow being taken away for the wastage and out through the digester there. So that is a nice way to at least make sure, sometimes for very complex plants that have a lot of flows splitting and combining and other things going on, I often use this as a nice visual double check just to make sure I've got everything set up the way that I intended. So you can see here, for example, that I can actually change the color of this. You can notice that this has come up in green. I was just playing around with that earlier today. Let's pick it back to pink there. And I can also change the thickness of the lines themselves. Now the reason we allow for this is so that you can see the relative difference. And it's a little bit tough to see here because these numbers are so much smaller than these numbers. We actually allow for some shading and other things that you can use to sort of get a handle on what's going on. But indeed, that is actually one of the issues with the Sankey diagram, is that often what's going on right here with the bioreactor and the secondary clarifier, these numbers will quite often be an order of magnitude bigger than all the other things that you want to look at. And for that reason, we allow you to actually turn these two things off here. You can do that just by coming to this area here and right-clicking and hiding that one. And you'll notice that as I'm doing that, it's going to rescale everything else. So now I've got a chance to sort of get a better handle on what's going on here. So that's flow. So let's go down here and take a look at COD. And we can see here that, of course, the COD coming into the plant, a lot of that COD is being taken out in the primary wastage, going to the digester, and so on. And if we're doing our job correctly, a lot of that COD is going to be removed and settled out in the clarifier and so on, and we won't have very much left in our effluent. So another fantastic way for you to be able to very quickly and visually illustrate to people how why primary sludge is important if you want to try and do some energy recovery in your digester and so on. So this is, again, a nice way to sort of illustrate what happens. You could potentially compare different options here in order to see how that is going to affect your solids line. So let's take a look at nitrogen. So again, there's some of that primary sludge is taking some of that nitrogen with it. We're fully nitrifying in this particular case here, but we're not denitrifying. So most of that nitrogen is staying in that system and going out with that effluent in the form of nitrate. And phosphorus, phosphorus, same thing. We're not really taking any phosphorus out because we're not doing any chemical dosage yet. So the idea behind this is that now we can see sort of our default situation. All right, so now let's take a look at dosing alums to remove that phosphorus. So I'm just going to rerun that again. And what I've done here now is in this alum dosage point here, I've now increased the amount of alum that from 0. Previously we were not doing anything, and now that's run again. So let's change this. Take a look back here at total phosphorus. And again, I have to just turn off that middle one. It's kind of interesting how it gives you a sense at steady state of how much phosphorus is stored in the system, that you have a line here that's so big that it kind of blots everything else out by its relative size. So now that's total phosphorus. So now we're precipitating that out. It's going out in the solids over here and out through the digester. So now this is the thick line instead of this one. And that allows us a very nice way to compare side by side those values. You can see here that we're looking at probably 5 times as much going out now through the digester as was previously going out in our effluent. Okay, and let's do one other scenario while we're at it. And in that particular case, we are going to keep the alum dosage on, and we are also going to denitrify. And the way that I'm doing that is I took this plug flow bioreactor here, and I took the first 2 DO set points and set those to 0, so we have a nice anoxic zone at the front of the tank, and I also have an internal recycle going from the back end of that plug flow reactor to the front end. So we're doing basically a simple MLE system here. And if I now go take a look, I can just verify that I'm actually denitrifying here. If I look at this little table, shows our ammonia going down from 25 down to 0.2, and we can see our nitrate is actually, it's about 0.5, so we're actually doing quite a good job of denitrifying there as well. So one last time around here, let me quickly turn off these little things in the middle here so we can get our correct scaling that we want. Okay, so now Again, flow, that basically looks the same, and we'll look at our total nitrogen. So now we can see here of that 176 coming in, you know, quite a bit of it has been reduced. In fact, it's less than 100 going out. So, you know, we're getting rid of a lot of that total nitrogen through denitrification. So, again, it's a really nice, fascinating way to sort of move things around and compare them side by side, which is what I'm going to do actually right now, back on my slides, just to really make it easier to see those things side by side. I just captured and copied the images out of GPSX, put them in the slide here. Here's no chemical dosage versus with chemical dosage for our phosphorus removal, and you can see here this, you know, most of it's going out in the effluent, or when we precipitate it out, it goes out in the digester. Those two ways there. So if in fact, if I put those side by side so that you can see the numbers a little more easily here, it's the same amount. If I add this number and this number, I get 44, same thing over here. It totally mass balances all the phosphorus, but you can see here that you know, 37 of that 44 pounds per day is going to go out when we're precipitating it out with chemicals. Okay, take a look at the same thing for nitrogen. If you can compare these two images side by side, you can see we're moving a relatively large amount of nitrogen from the effluent down to through the solids handling line, plus we're actually getting rid of a fair bit of it as nitrogen gas. Because we're denitrifying, and in this case, if I add 104 and 54 here, you know, we're looking at 157 versus 94. So that difference there is what's being lost to the atmosphere as nitrogen gas in the bioreactor, in those anoxic zones where we're denitrifying. So again, nice visual way to sort of tell that story. So what I can also do here is a few other things that can be changed or altered as part of your version of GPSX. The variables that are available to be plotted are actually listed here in this Excel spreadsheet in this particular folder. Now, you don't have to remember this pathway. This is available for you if you look in the GPSX user guide. It'll show you where to edit that file. And it's just a regular spreadsheet. You just open it up and you can add other variables that you would like to see here. And you can put their name as you would like to see them appear in the menu, and the units, your preference of units, whatever you would like to be able to use for the metric and the US systems in GPSX. So this is not only the variables that we have calculated, but if you were doing your own customization in a particular layout and you had a number of customizable models, say you've used our customization features or our model developer matrix tool that allows you to add other state variables to the system, and you're plotting another metal or something that goes through the system, you could add that to the list here, your customized variable, and you can make your own Sankey diagrams of that new thing that you've created and add it to the model. I'll just briefly mention that it's not exactly a Sankey diagram, but it's something similar. We have a couple of other new features here that are available just in the most recent version of GPSX. Our energy use summary button. It's actually right next to the Sankey diagram, and in the operating cost summary. They work a little bit in the same way. Essentially what they're doing is they take the image, as I was mentioning before, and then they plot on it a summary, a visual summary, not of the flow this time, but actually of the amount of energy use in each one of these particular objects. And you can click on them to find out how much of that particular, of that energy use is being used for aeration or mixing or heating or whatever. And also we can do it for, get a layout-wide breakdown in a pie chart like this. So those are also useful things to take a look at. So you can do it for just energy by itself, or you can do it for all of the operating costs in the plant. So that does include energy, but it also adds in sludge disposal cost, chemical cost, and any other cost that you've specified as part of our customization. So those are there and available for you to take a look at, and I'll probably maybe do a separate webinar on those on a different day. So just to summarize, it's actually a fairly useful tool for visualizing the way the nutrients move around through the plant. I kind of like it as a tool to convey the results of a modeling exercise to somebody else, particularly if they're not necessarily familiar with the details of GPSX. You can put up one of these nice diagrams that shows all the individual unit processes, and like I did earlier, plot a couple of them side by side for comparison purposes to show that, if we designed it this way or if we operated it this way versus that way, this is how things would be changed. It's also very good for debugging flows and very complex layouts. And by that I mean just using the flow session. If you have a controller, possibly say some PID control loops in there, and you've got maybe some algorithms that are used to control some flow splitters or what have you, with some bypassing and so on. You might have half a dozen or 10 splitters and combiners in your layout and flows going every which way. So it's very, very useful, I find, just as a nice visual double check to make sure that things are moving around the plant the way that you want them to. And as I mentioned, it's very easy to just export all of that information out and you can generate a report, or you can copy that image right into a report of your own very easily.